Swayam Prabha. Digital India. Educated India.
So, we continue with our discussion on processes and threads. You recall in the last two lectures we had discussed various aspects of processes, how processes maintain the state of execution of a running program, how we store or keep track of the processes, and as case studies for Unix or Linux systems, we also saw that how processes can be created, terminated, and the parent and child processes can synchronize among themselves. Now, most modern operating systems have the notion of threads in addition to processes. So, in this lecture we shall be trying to understand the concept of threads and how are they different from processes. Okay? Let us see. First, let us try to understand the basic concept of a thread. In a sense, a thread is very similar to a process, because it is a depiction of the execution status of a program. Some program in execution, as we said earlier that a process is a program in execution, a thread in a sense is also a program in execution, but it is a little, you can say, at a slightly higher resolution as compared to a process, which will be clear when you explain. So, we saw the notion of a process. A process is a program in execution. When you say it is a program in execution, during execution there are some processor registers, so you hold some temporary results of computation. There can be a program counter which will keep track of the next instruction to be executed. Because there is a single program counter, we say that there is a single thread of control. Why we say that? Because when a program is executing or running, depending on the program counter, a particular sequence of execution flow is carried out. If there is a sequential execution, one by one they will execute. If there is a branch instruction, it will branch to some other instruction. Depending on your input data, it will follow a single thread of execution. But talking about threads, we are actually talking about a slightly different scenario, which is called multi-threading. Because if it is a single thread, there is no difference from a process. The difference comes when you talk about multiple threads. Now, most of the modern operating systems, they do support multiple threads, specifically meaning that a single process can have multiple threads. That means, you have a relationship like this. You have a process, a single process, let us say a process P. A process P can have multiple threads, thread 1, thread 2, and so on. So, the concept is like this: a process was a unit of execution, so far we have discussed with respect to the CPU, but now I am saying inside a process you can create multiple threads. So, a process can have multiple threads of control. So, when I say multiple threads of control, it means there has to be multiple registers, there has to be multiple program counters, and so on. If there are 4 threads running, the 4 threads will be having different program counters, because they are doing something different, right? All of them are not executing the same thing. Okay. So, let us take an example. You will be able to understand that how this multiple threads can help with respect to a given application. You think of a word processor, that is an application, right? Word processor like MS or Microsoft Word or any other word processor. Now, in a word processor, when you type something, when you do some formatting, when you do some spelling check, so many things you are doing, right? So, as you are typing something, automatically grammar check, spelling check are carried out. In case of some apparent errors, some words are underlined to just warn you that please check the spelling and so on. So, there are so many things which are happening together, which possibly you are not being aware of. But if you think that when you type something, say you are doing formatting, right? You are setting something in bold, italics, changing the font size, changing the type of the font, automatically on the display the things are being reflected. So, there must be some program which is automatically updating the display depending on whatever you are requesting, right. At the same time you are typing something on the keyboard, there must be a program which is accepting the user inputs. As I said, when you are typing the inputs, sometimes you see that some words are getting automatically underlined, indicating that possibly there is some grammatical or spelling errors there. So, some spelling check is automatically going on. But in addition, not necessarily with a word processor, with some other application, some kind of network communication may be going on in the background. Let us say in a browser, when you are displaying some web page, something might get downloaded during that same time, some image is still downloading, some network communication is already going on. Now, you see there are multiple different things which are going on. Now, you can say that, well, I can manage all these 4 things in a single program. I can first take inputs from the user, then I will display, then I will do spelling check, then I will communicate on the network. Well, you can do, but you see the user experience suffers. Like when you are typing something, your display updation is not being carried out, your spelling check is not being carried out. Only after you have finished typing, the spelling check program will start checking. So, if there is a single thread of control, a single process, then you can do only one thing at a given time. But if there are multiple threads, each thread can be given a specific responsibility. So, while you are typing, that is one thread, another thread can be refreshing your display, another thread can be checking for spelling and so on. So, multi-threaded application usually leads to better user experience, that means your user responsiveness improves. Okay. Let us move into them into a little more detail. So, talking about a thread, exactly what is a thread, let us see. Earlier we said a process is like a unit of execution. In a system there are 10 processes, we divide our CPU time among the 10 processes. But now we are moving to a final level of granularity. We are saying that a thread is now a basic unit of CPU execution, not the process. There can be 10 processes, but there can be 25 threads running as part of those 10 processes. So, it is the threads that we want to manage, we want to run those threads on the CPU. So, instead of thinking that I have to run the processes, now I am thinking that I have to run the threads. Okay. Now, as I said, threads does not get created automatically. Normally from a process we create some threads, some other process we create some other threads, right. So, typically every thread contains a few things, like just like a process ID, a unique process ID, each thread will be having a unique number called thread ID. So, in short we can call it TID. And because every thread is a different so called thread of control, there will be multiple program counter values associated with every thread. Maybe one thread is executing this point in the program, another thread will be executing this point in the program, another thread will be executing this point in the program. So, the PC values will be different. So, each thread will contain a program counter value. Similarly, processor registers, because every time you start executing a thread, it will be starting to use the registers to store some temporary values and so on. So, the same register values cannot be shared by multiple threads. And of course, stack has to be different, because threads can call functions, and as I said, whenever there is a function call, some kind of activation record will get pushed in the stack. Some other thread may be calling some other function, so some different activation record will be put in the stack. So, if there are 4 threads, there has to be 4 stacks maintained, right. Now, there is something interesting about a thread. Suppose a process, same process, creates several threads. Now, some of the characteristics of these threads are as follows. See, when you do a fork to create processes, a new process, initially only the text section was shared, right. Data, heap, stack, they are all separate. But in a thread, the text section, data section and some other operating system resources, they are all shared. For processes it was not so, because of which the context switch for processes was more expensive. You have to save everything, you have to restore everything. But now suppose there are 4 threads which are running, they are sharing the code, the text, they are sharing the data section, they are sharing the files. So, when I move from one thread to another, I need not save those things, those can remain as it is. So, switching from one thread to other becomes much more faster. Essentially, all the threads that are generated from a single process, they share the same memory address space. Of course, stack will be different. Because such a thing is happening, for a thread, context switch overhead is so much less, much faster as compared to a process. You have to save so few things as compared to so many things in a process. A thread is sometimes referred to as a lightweight process, because the overheads of implementation of a thread is less as compared to a process. As I said, context switch is much faster. That is one big advantage of a thread. Now, pictorially let us show how a single threaded process and multi-threading actually differ. The diagram on the left refers to a single threaded process, which is our conventional process, as we had seen earlier. Now, here this red arrow indicates a thread, right. So, for a single threaded process, there is only one thread, which is thread means a single thread of execution, some sequence of instructions which are executed, there is a single thread of execution, that is shown by a single arrow. Now, this process contains so many things. It contains a code, it contains data, it contains the list of open files, registers, stacks, and of course, heap is also there. I am not showing heap here. So, if there is another process, they will have a similar thing, code, data, file, register, stack, everything will be different. Okay. This is for a process. If there are multiple processes, the same thing will get replicated several times. But now, in the diagram on the right, you think of a multi-threaded process, where there was a process let us say, which has created 3 different threads. This is your thread 1, let us say, this is your thread 2, this is your thread 3, and these red arrows indicate that they have 3 different threads of control. Whatever thread 1 is executing, thread 2 is executing something else, thread 3 is executing something else. But the point to note is that you see the first part on top, this part, this is something which is shared. All the 3 threads share the code, share the data, share all open files and stuff like that. Everything is shared. So, whenever you move from one thread to another, you need not change the code or data or files, they remain the same. But the things that differ will be the registers and the stack. Each of the threads will have to maintain separate register and stack values. So, when you do context switching of thread level context switching, you have to save and restore the registers and the pointer to the stack. That is all you have to save, nothing more, right. This is why I said for switching of threads, the overheads are much less. That is why you will see that most of the modern operating system, they support multi-threading, and many of the current applications also take advantage of that. Okay. Now, let us look at some of the benefits of threading. Couple of them we have already mentioned. First and foremost is that context switching among the competing execution units is much faster. For multi-threading, the competing units are the threads. Switching of threads, stopping one thread and starting another thread is much faster as compared to stopping one process and starting another process. The reason is that the operating system needs to save and restore less data. Okay? Because in traditional processes, memory, registers, process state, so many things have to be saved. And secondly, with the help of the example, I said that it can lead to better responsiveness of applications. Typically, for applications which are interactive, interactive means the user is sitting in front of the computer and doing something. So, what is the expectation of the user? Whenever you do something, you need immediate response coming on the screen. So, you type something, you will not like if the thing comes on your screen after 5 seconds, right. You want immediate response. So, if you have a thread which is dedicated for your user input, then the thread will continuously read data from the keyboard. You will not have to wait because something else was going on in the system, some spelling check was going on or something else was going on, right. And since the code and data regions in a thread are shared, as I said, it leads to better resource sharing among the peer thread. Peer thread means, so when I say peer threads, it means all threads which are generated from the same process. From the same process. So, you can have multiple threads of activity I have said. Since the data area is shared, you can directly share variables among multiple threads. One thread can write data into a variable, another thread can read data from that variable. Right? So, more efficient sharing of variables is possible, but later on we shall see that when you share variables like this, some problems may occur for which you need some locking mechanism when you are updating the value of a variable. This we shall see later. Okay. And Another important thing is that a process is already there. When you are creating a thread out of a process, you need not create all the regions, right. That is why the creation of thread is much faster as compared to the creation of a new process. Typically, it can be 10 to 30 times faster. Okay. So, in terms of efficiency, it is better. And lastly, it provides better scalability. Scalability means, you say nowadays we are moving towards multi-core architectures. Number of cores are increasing every year, and also we have multi-processor architectures. So, when you have such an architecture where the number of processors and the number of threads that it support can increase very rapidly. So, this multi-threading concept can give you a platform where that increase in the capability can be exploited. Now, in fact, all modern day processors, they have direct hardware support through which you can carry out some kind of multi-threading. Okay? Fine. Now, let us look at a couple of applications where multi-threading can be used. In fact, it is used in the modern applications that we use daily. Let us think of a web browser. Think of web browser like the Chrome, like the Mozilla, whatever you use, they do something very similar nowadays. What they do, browser is something where a user is always sitting in front. It has to be interactive. User responsiveness has to be very prompt. So, what browsers do, the browser application, they have support for multiple threads, where each thread is having some dedicated functionality. The primary reason is to provide better user experience. This is most important. Nowadays, users are not that much concerned about how fast my computer is, but how responsive my computer is when I give some command, that becomes more important. Okay? Let us say for a web browser, you can have one thread that can be downloading some files from the network, not one, maybe more than one also. If a web page contains multiple images or multiple such stuff, maybe some image file, some video file which needs to be downloaded, you can have multiple threads which may be downloaded them in together in parallel. Okay. And whatever is being downloaded, they have to be displayed properly on the screen, because typically when you download some stuff from the internet, they are usually in HTML or some other kind of an object embedded in HTML. Okay. So, you can have another thread or threads which can render the web pages, display it properly after they have been downloaded, right. And in a browser, you may be clicking on the mouse, you may be typing something on some forms on the page. So, there can be another thread or threads which can be responding to the user inputs. Okay. So, there can be many more. There are so many tabs you are opening on the browsers, there can be one thread corresponding to each tab, right. So, you see, if you have this multi-threading support in a browser, your user experience is bound to improve, because you are not waiting for anything for something else to complete, because everything apparently is going on together by the different threads, and the CPU time is efficiently being shared among all the threads. Okay. Let us look at another example of a web server. Now, what is a web server? A web server is a machine where the web pages are hosted or they are stored. From the browsers, from different places, people access those pages from the web server, right. Those are sometimes referred to as web clients. The browsers are referred to as clients. There can be multiple such browsers. they may be sending some requests to the server, and the server may be responding with the response. They may be sending back the requested information back to the clients. Now, in general, a web server, I mean the popular web servers, you think of the popular web servers, they may have to respond to large number of client requests, possibly many number of requests which are coming simultaneously. So, this is one important point. A web server may need to service a number of simultaneous requests from a number of different clients, that means browsers. Earlier, if you look at the web browsers that were there in the first generations, old versions of the web browsers, they used to create multiple processes. The idea is like this: suppose I am a, let us say I am a web server. What I am doing? I am waiting for requests from clients. I see that a new request has come. What I do? I fork a child process and ask the child process that please contact that client and respond whatever request he is sending. Another request comes, I fork another child process and ask the child, you directly contact this new client and send whatever that client is asking. So, if there are 100 requests, there will be 100 processes that will be created. Now, as I said, creation of processes, management of processes is not so easy, it is expensive. So, the earlier generation of web servers had some restriction regarding the maximum number of simultaneous connections that can be accepted, because creation of processors require memory and memory was also limited. Okay. They were expensive in terms of resources, but nowadays in the modern generation they do not create new processes, rather the server process can create threads. It says each thread will be handling one user request, because threads are so lightweight, they require much less memory and other resources, they will be much more efficient, and the server will be able to handle many more client requests as it used to do earlier. Okay. So, this is one application where you can see multi-threading support can lead to a significant advantage. Okay. Now, talking about threads, thread support in a system, I mean I am talking of an operating system, can happen in one of two ways. We refer to them as user level threads or user threads, kernel level threads or kernel threads. Well, you recall the general structure of an operating system. There is some kind of a boundary. On one side of the boundary you have the kernel. These are the critical operating system routines. On the other side you have the user programs running, the applications. So, whenever the user programs require something from the operating system, it sends some request to the kernel, right. This is what they do through something called system calls. Now, user thread, what I am saying is that all thread management activities, like see when we talked about processes earlier, we talked about creation of processes, termination of processes. We mentioned that processes may need to communicate, but did not say how. This we shall be discussing later. Similar things are required for threads also. So, when I say thread management, we talk about creation of new threads, deletion of existing threads and multiple peer threads communicating among themselves, inter-thread communication. Now, in the simplest case, this communication can happen through shared variables. One thread can write some data into a variable, other thread can read the data from that variable. Well, we shall see an example a little later. Now, these management are carried out using user level thread libraries. Means, as a user you are writing a program, some library functions are provided to you. You can directly call those functions. You can create a thread, you can delete a thread and so on. So that you can write your own application that involves one or more threads. This is user level thread because as part of a single process you are doing all these things. You are calling the library to create as many threads you want, and each of the thread will be doing whatever you want. So, there are many thread libraries, user level thread libraries that exist. One of the most commonly used library, where we shall be giving an example also, is POSIX pthread, right. Now, other than user level threads, you can have kernel level threads also, which means, see, normally so far whatever we have said, what does the kernel do, what does the operating system do? They take the processes as the fundamental unit and they share CPU time and resources among the processes. We talked about a process state transition diagram, but when we talk about kernel level threads, we are saying that switching of the resources among the threads are directly done by the kernel. So, instead of managing the processes, kernel is now managing the threads. So, this kind of thread management here is directly supported by the kernel, and because the kernel is very protected and very highly optimized, it will be much more efficient as compared to user level threads. And almost all modern day operating system, they support kernel level threads. Like some examples I am giving: Linux, Solaris, Windows, Mac OS, different versions. So, all of them they support kernel level threads because they are so efficient, and also they are also very secure. Okay. Now, the point to note is that even if you are using user level threads, you have created threads using user level calls, but you will be relying on the kernel to provide CPU time to your process, and within that allocated time all the threads will be given some time. So, ultimately you will be needing some kernel thread support, because without the kernel you cannot give the CPU time to different threads, because the kernel will be giving some time either at the process level or at the kernel level, and then all the user level threads you are creating, you can share your time among them. Basically, user level thread means some functions are provided to you as the user. So, you can write your application in whatever way you want. Explicitly you can manage the threads, you can create thread, you can delete thread, you can communicate among the threads, instead of relying on the kernel to do everything on your behalf. Okay. Fine. Now, let us look at the various multi-threading models, like there are user level threads, there are kernel level threads. In these diagrams, this red arrow we are using to represent user thread, and this circle with K written inside is referred to as, or this indicates a kernel thread. Now, there can be multiple possibilities. One possibility is the first diagram on the left, many to one. Many user threads are mapped to a single kernel thread. See, this is a little old concept. Today you do not see this, because today almost, as I said, almost all operating systems, they support multi-threading in the kernel, but this many to one diagram says that you have a single kernel thread running. That means, it is like a normal process scheduling, one process at a time, one kernel at a time, I mean one thread at a time. So, if there are multiple user threads and one kernel thread, so one of the threads can be scheduled to run at a given time. So, this is very similar to traditional process scheduling. So, thread and process does not make much difference, but modern day operating system, they support one of the other two, some support both. First one is one to one. One to one, the idea is the kernel gives support for many number of kernel level threads, and through user level thread library, possibly the user applications are also creating multiple threads. So, each of these user level threads are having a one to one mapping with the kernel level threads. So, each kernel level thread is assigned the task of handling one user level thread, right. This is a very simple concept. And the other concept is that instead of giving this one to one responsibility, because in a system the number of user level threads can become very large, possibly the number of kernel level threads that are supported is not that large. So, you can separate these two out, like on one side you can have the user level threads, let us say m in number. On the other side you have the kernel level threads, let us say n in number, where in general m and n are not equal. Typically m would be greater than n. For a system with many processes running, m will be greater than n. So, what is done? Any of these user level threads can be mapped to any of the kernel level threads, and that can change with time. Let us say the first thread was assigned to this kernel here, this thread. Sometime later it may be assigned to the second thread. Okay. So, this is a more general scenario, and as I said, the modern day operating system, they support the one to one and many to many models, many of them. Okay. Now, let us look into a specific case study. One user level thread, not necessarily user level, POSIX P thread also supports kernel level thread. So, the examples that we shall be showing will be for user level thread. Let us see what this POSIX really is. The pthread library, this is the name of the library, pthread. This pthread library contains a number of functions that you can call from your given application. Essentially, this pthread library allows your application to have threading support, multi-threading support. And as I said, you can have either user level thread or you can also have kernel level thread. Both versions are supported by pthread, right. Now, the example that I am showing here will pertain to C or C++ kind of programs. Now, in a C program, if you recall, for those of you who are familiar with C, that a program can consist of a number of functions, like you have a function here, another function here, another function here. So, all of them make a program. Now, you can define some data, some variables inside these functions. You can define some data inside these functions, or you can also define some data outside these functions. So, whenever you define the data outside the functions, those data values will be made available to all the functions. Those are called global variables or global data. But when you are defining some variables inside a function, they will be referred to as local variables or local data. They cannot be used from outside the function, they can be used only from within the function, right. So, with respect to pthread, there is a concept of global data and local data. So, it is very similar to what I just now said. Global data means any data or any variable which you have declared globally. Declared globally in a C program, as I said, global data can be shared by all functions, but here with respect to multi-threading we are saying global data can be shared by all threads. All the threads can share global data. Similarly, you can have local data. These are the data that are defined inside a thread, or a thread may be calling a function, data defined inside that function. These are all local data of that thread. Just like I said earlier that for a normal running program or process, whenever there is a function call, there is an activation record which gets saved in the stack. So, in a similar way for a thread also, whenever you are making a function call, the activation record containing all local variables will get saved in the stack. Okay? Fine. Let us work out a complete example in C and see how we can create threads and how we can do several kinds of thread management. Now, we have taken a very simple example as illustration. Suppose what we want to do, we want to create the sum of n squares of n natural numbers, like we want to find out 1 square plus 2 square plus 3 square plus n square. Well, here of course, you know that there is a formula for this. You can always compute this using a formula like this, but assume I do not know the formula. I will directly go on adding 1 square, 2 square, 3 square, 4 square up to n square to find the sum. So, what I will do, there will be a parent thread, there will be a parent that will be creating a child thread. So, only one thread we are creating in this example program. The child thread will be computing this sum, and there will be a global data that we are defining. After computing the sum, it will store the sum value into that global data, and the parent what it will do, it will simply take the data out of there and print it, but it will check whether the child thread has terminated or not. Terminated means this calculation is complete, it has stored the data, only then it will print, and the value of n is also provided as an input to the user as a command line argument. Command line argument means, let us say whenever you run this program, normally you give the name of the program, let us say my prog. You can give a number 10, this 10 will be the value of n, and if you give an input as part of the same line you are giving a command, that is called a command line argument. And as I said, the parent will wait for the child thread to terminate, only after that it will print that value, because the parent otherwise will not know that whether the value has been computed or still the child is in the process of computing. Let us see. This is the first part of the code, there is a little more to it. Let us just understand. This is a C program. So, we have included the standard IO library that we will need for all printing and other standard functions. To use the pthread library, you have to include this header pthread.h. This is the first thing. Now, you see in this program code we have defined a function here main, and we have defined a global data outside the function int sum of sqr. That is a variable we have defined here, this one. This is a global data. So, the child and the parent, both of them can access that data together. Now, here we specify a function prototype. Function prototype basically means we specify the name of a function. It is a function pointer star compute, and it takes a parameter, this is also a pointer n. Basically, what I am telling is that the child process that will be created, that will be calling this function compute. This compute is on the next slide, I shall be coming to this. This is the compute function, but this is the function prototype. You have to specify function prototype in a C program, that how this function is, what are these parameters and return values. Now, let us see the main function. Main, because we are passing command line arguments, we are writing this int argc char star argv, because argv1, that 10 I said second argument, that second argument I can access as, like for example, I gave that example my prog 10. So, if I want to take this value 10, I can refer to it as argument value 1. My prog is argument value 0, 10 is argument value 1. My prog is argv 0 and this is argv 1. We actually need argv 1. This is how command line arguments can be accessed. Let us see inside this main function what we have done. We created a variable called TID. In the pthread library, the data type for our thread ID is given, that is called pthread underscore t. So, TID is of type pthread underscore t. Then we define some attributes of the thread, we give a name to variable, let us say we give a name attrib, and this is of a type thread attribute. So, in that pthread.h, that type is also given pthread underscore attrib attr underscore t. Now, we initialize the attribute. What are the initialized attributes of the thread? We make a call to this function pthread attr init, and we pass a parameter attribute address of that as parameter. So, it gets initialized, and the initialized value of the attribute also gets stored in attrib, that structure. Attrib is actually a structure. Then we can create a new thread by making a call to pthread create. When I create a new thread ID will be created. Every thread will be having a unique thread ID. So, I am passing one parameter ampersand TID, address of TID. So, the new thread ID that is created, that will be stored in TID. I can use that in the program later on. Similarly, this attrib, I am passing the address of this attribute. And what is this thread? The child thread I am telling, actually you will have to call a function called compute, and as a parameter you will have to take argv1. So, compute will be function, and in place of this n, the value 10 if you give, that 10 will go as n. And then the parent process will be waiting till the child is complete. For that you will be calling a function called pthread join. You will be passing that thread ID which was returned as a parameter. Second parameter is null, do not worry about it. And when the child terminates, this pthread join will come out, and then only this value will be printed. This global value sum of SQR, that value will be printed. Okay. Now, let us see the function compute, what it does. Function compute is very simple. It simply takes this is a function pointer, the way it was defined. The parameter was also a pointer n. Now, when you use a command line argument that 10, that 10 is read as a character string, not as a number. So, you will have to convert it into a number. So, we do it here. ASCII alphanumeric to ASCII to integer. So, the value of n, we convert it to integer, we store it into a variable num, and here we simply calculate the sum of the squares. That sum of SQR, that variable was defined in global, that same global variable is used. So, I store the result in global, and after we finish, this child thread must exit. We call a p thread exit with a value 0 in case you need the return value. Okay. This is how. Now, you see in the previous slide, when you use this p thread create, you can create as many threads as you want. In a for loop, you can create 10, 100, 1000 threads as you want. Each of the 100 threads you can say that what you want to compute with what parameter. So, it is entirely up to the user to write this code and to specify exactly how this has to be done. Right. Now, this is what I am saying, that you can create as many threads as you want by calling p thread create as many times as you need. So, in general you see what you are doing when you are using the user level p thread library, you have an original process, right. This is your original process. Inside the process, you are creating so many threads. And when the operating system normally scheduled processes, it will give each process a time slice. Let us say 2 milliseconds. And within this 2 millisecond time slice, all the threads you have created inside, they will be assigned some time. Let us say these threads will be assigned, each of the thread, let us say 0.25 milliseconds each, let us say. So, there will be one special thread also created that will be responsible for scheduling the threads. So, there will be one scheduler thread which will be responsible for scheduling these thread operations. Okay. So, this is generally how thread scheduling works. We are not going into any further details of thread scheduling, but the basic idea is important. In a system we have processes, from the processes we can create threads, and threads can be scheduled on the processors because most of the processors support multi-threading nowadays. Operating systems support multi-threading. Okay. And many of these modern day architectures have multiple register banks. So, the switching from one thread to another becomes very fast. Okay. So, where we have seen the concept of processes as programs in execution and the concept of threads as well as finer threads of execution inside a process. But in the next module, what we shall see, which we have not discussed so far, that when you have this kind of concurrent processes or threads, similar concepts will appear. How do we synchronize them? How do you make them communicate with each other so that any meaningful applications can be built? This will be the topic of discussion in our next module. Thank you.
Prabha.